Good morning, everyone. So I'm Jérémie Cohen. I'm a pediatrician and researcher in clinical epidemiology. And today I will present one of my students' work, Constance. She's not here today, unfortunately. And it's about the development and validation of a smartphone-based deep learning system to detect middle ear conditions in digital otoscopic images. So a bit of context. So external and middle ear conditions lead to many consultations, mainly in primary care. And if left undiagnosed and untreated, they may lead to hearing loss and infectious complications. So the main concern in children is otitis media because it is associated with inappropriate antibiotic use. At the moment, diagnosis is mainly made by otoscopy, so inserting an otoscope in the ear and looking at the tympanic membrane. But we know that otoscopy has poor accuracy because GPs and pediatricians do not do it really well. So the accuracy is usually around 70%. So what we intended to do is to develop a system based on AI that could lead to improved diagnosis of external and middle ear conditions. The idea was to have a tool that could be used by non-ENT specialists, so GPs, for example, and to be used in children and in adults, with the aim of guiding medical management, for example, for prescribing antibiotics or referring to an ENT specialist. So the project started when we met this ENT specialist, Dr. Schmoll in Strasbourg, and in fact he was doing digital otoscopy for many years in his office already, in all patients, mainly patients above 5 years. He was using an otoscope from Karl Storz, a German provider. And as you can see in this image, this is Laurent Schmoll. He's doing digital otoscopy, and as you can see, he has this otoscope connected to his iPhone, and he's taking pictures of what he's seeing inside the ear. The great thing is that Dr. Schmoll made this data set and collected thousands of images and then labeled them across 11 diagnoses. So, for example, you can see images from his collection, normal ear, wax plug, acute otitis media with perforation, this one, and cholesteatoma. So these are examples from his collection. And when we looked a bit closer, we found that he had two data sets that he was willing to work on. One was data set number 1, with about 100,000 images from digital otoscopy. This dataset was really unbalanced, so some categories were underrepresented, so we balanced the dataset and obtained something around 45,000 images that could be divided in a training set and an internal validation set, a test set. And then he had another collection of images that he took later on, and because at this time he was almost not using digital otoscopy for his collection, this collection is smaller, so he has only 326 images, but we thought maybe we could use it for external validation because it was collected at a different period of time. So what we did is that we teamed up with a partner, Clarify. So Clarify is one of the leaders in computer vision, actually not really in medical image analysis, but more trying to build autonomous cars, for example. And with their help, we conducted this study step by step. So first image pre-processing, exclusion of images of poor quality, resizing and center cropping of images, data augmentation with random rotations and flips. And then we analyze the data with an architecture that is Inception v2, developed by Google. The programming was done in Python. And as discussed this morning, the model was pre-trained on ImageNet, which is a very large collection available of images available on the internet, with hundreds of different classes that are labeled. And in the end, the model has about 5 million parameters. And the final step was to work with a company that Laurent Schmoll also founded, and to build a smartphone app that can implement the model. So the application is available, it's called Insight. So if you look a bit deeper in what the model does, it's a typical model of computer vision. So if you start with this kind of image, this is a digital otoscopy image. So this one is, you see, about 100,000 pixels. For the sake of simplification, I'm going just to put it in grayscale. And actually, what the computer sees is numbers. So it will take small parts of the image and transform it into a grid of numbers. And the numbers are a representation of pixel intensity. So imagine that this is a patient, and now it goes with 100,000 variables. Each pixel is considered a variable in the model, and each pixel is represented by numbers. So each image is represented by a grid of numbers. Okay, this is the basic structure. And then this is also a schema of what goes on in the modeling steps. So you start with an image. The image is transformed into grids of numbers. And then you apply transformations on this grid of numbers by alternating pooling layers and convolution layers. And then you end up with a small vector of numbers. So you start with a very large grid of numbers, let's say 100,000, and you compact it into a small vector of numbers. And from that vector, you try to predict the diagnosis, and you can have as many classes as you want in the fully connected layer at the end. You just use a softmax function, which is a kind of logistic function, but with more classes. And the output is that you get a prediction between 0 and 1 for each of the classes. If you continue and try to get more information about what's going on in the neural networks, well, the convolution layer, what is it? It's the idea of applying a filter, so a transformation to the image, and trying to keep the most predictive filters. So the aim is to start with input images, and then extract patterns that predict diagnosis in the images. So, in fact, I think you know this because it's used in most image processing software that you may have on your computer. So you start with an image, and then you apply filters, right? So, for example, you have the sharpen filter, so it's just a filter that sharpens edges. And then you have the sobel filter, for example, that is a filter that enhances horizontal lines. So it's exactly the same. You're just applying a filter to the image and keep the most discriminative filters. But what exactly goes on is something like this. I'm sorry, the image did not go well when it was imported. It should not be exactly like this, but it's not a problem. I think we can sort it out. So you have the input image on the left, which is a grid of numbers. And then you're going to apply a filter, and the filter is another grid of numbers. And you're just doing a very simple linear combination. So, for example, here you start with the pink image on the left, you apply the blue filter in the middle, and you do a linear combination. So the first number that is missing is is 1, times -1, plus 2 times -2, and numbers add up to 8. So instead of having a 3 by 3 grid of numbers, you just have one number. So you're reducing the size of the vector. The second type of layer is called a pooling layer, and again, it's very simple mathematics. So you're just taking the maximal value in an area. So remember that the numbers are pixel intensities. So you're taking, for example, the first square, the 2 by 2 square, and you extract the highest number, which is 8. And then you move the filter to the right. Again, a 2 by 2 small table, the maximal number is 3, and then you move down 5 and 5. So you have, again, reduced the size of the representation by extracting some numbers into it. So after alternating all these layers, you have predictions. So the model gives you a prediction between 0 and 1 for each of the classes. And in a diagnostic accuracy study, you can define an index test and a reference standard. So the index test is going to be the prediction made by the model. And here you are going, what we did is that we took the diagnostic class with the highest prediction. The reference standard is the diagnosis made by the specialist, which is sometimes labeled as ground truth. And then you build contingency tables. But the first problem, let's say, is that it's not a 2-by-2 table because we have 11 diagnoses that are possible. So it's an 11-by-11 table. And because of that structure, you cannot calculate sensitivity and specificity, but we decided to calculate class-specific estimates of sensitivity and specificity, and also we could draw ROC curves. We conducted internal and external validations, and also a graphical approach. So this is an example of a reduced 11-by-11 table. So each time you want to compute a class estimate sensitivity and specificity, you have to extract the true positives, false negatives, and true negatives by grouping categories together. And here are the results. So this is internal validation, so on a subset of images, about 4,000. And as you can see, the model was making almost perfect predictions for all classes with sensitivity and specificity very close to 100. So we could have stopped here and we could have said, well, this is just perfect. It's almost never making mistakes. But we had the luck and bad luck of having an external data set for validation. And here the performance went down. So specificity remained very high for all categories, but sensitivity was acceptable for some categories, but very low for others, and was as low as around 30% for the presence of a foreign body in the ear, for example. This is another approach that is called T-distributed stochastic neighbor embedding. So it's a visualization of high-dimensional features extracted by the model. So it's a kind of clustering, just to see how the model clusters the images together or not. And as you can see, there was, well, for some categories, the clustering was very strong, but for some other categories, there was overlap, and this is reflected in the poor accuracy for some categories. So again, sorry for the presentation. I think there was a miscommunication with my USB stick. So the nice thing in this project is that we have an end-to-end diagnostic system. So you have a digital otoscope, you have a model, and you have a smartphone app. So this is readily available. I use it sometimes. We have leveraged a very large digital otoscopic data set, and we have used state-of-the-art deep learning techniques with convolutional networks. We had an external validation data set, which is quite rare in the field. Limitations, well, obviously, this is a monocentric and retrospective study. The digital otoscope that is used is of very high quality, but it's very expensive. So it's about 4,000 euros, so it's not scalable. I mean, people cannot buy it like that. But I have tried with a lighter otoscope, which is about 1,000 euros, and it performs really well. So maybe in the future, the price will go down, and we can use it every day. Another limitation is that no child under 5 years was included, and this is a problem because this is the group where it's the most challenging to perform otoscopy, because little children, they move, they hit you, they scream, so it's difficult in this population, and this is a population we didn't have in this more kind of proof of concept study. And the validation data set used for external validation was a bit limited in size, and especially some categories, we only had 10 pictures. So at the end of the journey, what did we learn as clinical epidemiologists, because this was the topic of today? Building AI diagnostics is very interesting, but it may require very large data sets. This is not always easy to obtain. It also requires advanced data engineering in software such as Python, for example, which is can be a bit more tricky than R, for example. We also faced a challenge because we had the multi-class classifier, so the sensitivity specificity paradigm does not really hold in this case. There is also a risk of overfitting. So if you have a very large data set that is not very diverse, you will have overfitting. So as you can see, internal predictions were great, but when we tried with a slightly different data set, well, the performance went down, and this could be mitigated maybe in a future iteration of the software with penalizations, for example. Another challenge is that the field evolves very quickly. So the time it took us to make this work and publish it, our model was completely outdated. And of course, every week, every month, you have dozens of new AI models that are published and readily available off the shelf, for example, using Hugging Face. But for academic actors, we need time because we need ethical clearance, we need funding, we need to think, we need to analyze, we need to write, we need peer review. So it's different time scale, and this is very challenging, I think. Another message is that teamwork is key in such initiative, especially with multiple stakeholders, including industry, and we could not have done that if we had not partnered with Clarify and Insight, for example. Thank you very much.
Thank you, Jeremy. Very nice presentation and very interesting project. I have a question. So, you assigned you based the classification on the probabilities, but that means that you treat a case where there's 100% certainty that this is the diagnosis the same way as a 60%, while the 6% is higher than all the rest. Have you actually looked, for example, at the calibration of the calculated probabilities as another way of evaluating the performance of your predictions? Mm-hmm. And the second question, if I may, have you actually discarded the poor quality images? I would be interested in looking at the performance in the discarded images as well, because that's what happened in practice with inexperienced physicians. Mm-hmm.
Thank you, Patrick. So for the first question, at the moment we didn't look at calibration. We were only asked to produce class-specific ROC curves, but yeah, maybe looking at calibration and discussing the threshold would be interesting when we look back at the project. And for the second question, sorry, what was it again? Applying the algorithm of low quality. Yes, thank you. So yes, looking back, I think this was a mistake. So the problem that we have in this data set is lack of diversity. So we want more diversity in the images when training such models, because otherwise there is overfitting and it doesn't work well when the images that you try in the second step are of low quality. So this was raised by one of the peer reviewers, so I could not present this today, but we used adversarial attacks on the images. So there are also ways of blurring and generating low quality by lowering the resolution of images, by suggesting a move, by having out of focus images, and you can create that with generative AI and adversarial attacks. So we did it, and it didn't change much in the end.
Yeah, thank you for the very nice presentation. I had two related questions. So the first one is, so did you try a simpler machine learning model like logistic regression just to have a baseline and to know where you can go? And my second question is about so your CNN, convolutional neural network. So how did you choose the number of hidden layers and so on? So how did you choose your hyperparameters?
Mm-hmm. Thank you. So for the first question, we did not try logistic regression because it was well proven for now a bit more than 10 years that convolutional networks outperform any other machine learning, let's say, algorithm on computer vision. So every year there are competitions, and if with this, I think this kind of model usually outperforms logistic regression.
Yeah, but if
We
I
could
may,
try.
it gives you a baseline, so you know which accuracy you can expect. Of course, you expect more with CNN, but at least it gives you an idea on whether. Yeah. Okay.
Yeah, good suggestion. We can try it. And the second was, sorry?
It was how did you choose the architecture of your CNN, the number of layers? And,
So what we did is that we wanted not to do so much engineering on the architecture. So we just took Inception v2, which is an open source model from Google, and we applied it with very minimal tweaks, but that was just for saving computation time, for example. But otherwise, we really applied Inception v2 off the shelf. You can just download it from Hugging Face and use it. So we also tried, of course, this was a comment from one of the peer reviewers. Actually, I think Inception v2 is from 2015 or something. So it took us almost 10 years to finalize this. But in the meanwhile, many models were published, including vision transformers, for example. So we also tried a dozen of others, of other more recent models, and the incremental accuracy was minimal. So really minimal. Less than 1 point in accuracy, for example.
Thank you.